In order to keep this a bit short, Chris is currently a co-PI at Julia Lab at the MIT and also director of modeling and simulation at Julia Computing, and a well-known figure in the Julia world, known for packages such as differential equation and SciML. So, Chris, go ahead.
Oh, yeah, sorry about that. Yeah, so I'm going to be talking about how equation solvers are integrated with probabilistic programming languages. And essentially my thesis here is going to be, Turing is arguably both the most extensive differential equation solver support, and it has absolutely none. There's no middle ground with Turing here. So how are both of those statements true, but the middle is not? And so what I really want to do is I want to first describe what extensive differential equation solver support can mean. And then I want to describe how, what does Turing actually have, and where does it get to, and what kind of consequences does that have on users of the language and its structures of Turing itself. So first of all, you might, I know that this is not like an equation solver group, right? So ODEs are simple, right? You just call an ODE solver, right? So here, for example, is the Lorentz equation. You define your ODE just in terms of values on an array. You call, you build an ODE problem, you call solve, there you go. That's an ODE solver, right? And every probabilistic programming language sooner or later gets this ODE solver, right? Maybe not this exact one, maybe one of the older versions like the Dorman-Prince method, but there's something at least similar to that, right? But that's not all that ODEs are, right? So why would you need more, right? Why would extensive support matter? Well, the first thing that you could think of is, yes, there's a whole lot of different optimizations that can matter. So here, for example, this is using static arrays. So using a statically compiled ODE solver that's recompiled to the given problem can cause about 5x in performance. And so, you can sit down with ODE solvers and these go, okay, even just for non-stiff ODE solvers, there's Vern7 versus Dupree 5 versus SIT 5, and they, you can line them up and see how, different non-stiff methods all change performance. But it's not really just all about performance, right? So there's a lot more to what people need with ODE solving than just this difference of, okay, we could be performant here, we could be performant here in all those cases, right? This is why someone might look at, like looking at a differential equation solver library and go, oh, I need to call that because it's fast in some sense, right? But there's more to that, right? And for example, when you get to thousands of ODEs, what actually causes these differences? What are things that you need to think about for these differences, right? And one of the major things is that there's a lot more different ODE solver algorithms, and they matter for different domains in different cases, right? So the first thing that comes up is stiffness, right? So stiffness is this behavior that can happen with a evolving system where you can have differences in time scale. So let's say the true solution is supposed to go along this path, and you have a very large derivative, right? So basically what you need two different time scales. You need a large time scale and a small time scale. And in the small time scale, you have things, wiggling. And in the large time scale, you have some kind of average movement, right? The true solution will just be the average movement. Everything that I show here is an aberration of a standard ODE solver like Euler's method when you extrapolate forward using the local derivative. What this tells you is that the local derivative information is not good information. You need to somehow average the slope up with the slope down, right? And if you average that out, then you find out that you get a smooth solution. And so stiff equations are problems for which the easy methods don't work, is another way that someone in the field actually defined it. And so, okay, if that's the case, then you have some problems that are harder than others. So then you just have a stiff differential equation solver as well. Rodas 5 is a stiff equation solver. So you define an ODE that is now stiff, you call the other solver and you're good, right? So, okay, maybe you need more than two. Maybe to optimize performance, why would this be a bigger deal? So then there's cases that aren't necessarily stiff or non-stiff, right? So you have this interesting case here. This is from a magnetic dipole PDE, which has some properties that are stiff-like, but some properties that are not. All of its eigenvalues are real valued, and so therefore there are some integrators that aren't for stiff equations, but specialized for this semi-stiff mode. So here's Rock here's rock 2, you can see that becomes the most performant in this kind of regime. And so you go, okay, now 3 solvers, right? Maybe that's all you need. But then it turns out that there's tons of other different properties that can occur when trying to look at equation systems, right? So symplectic integrators are something that people who implement PPLs know about symplectic integrators, because they're actually used for the Hamiltonian Monte Carlo integration algorithm. I'll go over that in a second. But there's also a lot of other special forms, Magnus integrators for A of t times u, that also preserves positivity and other features. Bethune-Coutts methods, Nystrom methods are like Runge-Kutta methods, but they actually have about a 50% performance improvement for second order ODEs. There's exponential integrators when you have a semi-linear term. So when your ODE has one matrix times a vector plus something else. There's implicit explicit methods for if only half your equation is stiff. And so there's a lot of different cases that can come up when solving an ODE, and using the right integrator could be crucial, not just for performance, but also for getting the correct answer. And one nice one for that is to look at, for example, symplectic integrators. This is a question on computational science Stack Overflow that I gave. And so if you want to see the details on symplectic integrators, just search this right here, and you can find this discussion. What happens is that if for very long time integrations on a Hamiltonian system, you should expect that your system will be in some sense quasi-periodic or something, but a standard integrator does not necessarily have a solution that lives on the symplectic manifold, and when that causes that causes a essentially linear drift over time in what should be conservation laws. In symplectic integrators, you end up having that your first integrals are exactly preserved. So, for example, on the Kepler problem of a two-dimensional dynamics, you have your angular momentum is preserved. You actually do get some drift in the energy. So people who say that they're energy preserving, that's actually incorrect. But it is the energy drift is in some sense periodic, and it drifts out in a way that is very slow in comparison to standard integrators, right? So if you want to integrate over a very long time frame of a Hamiltonian system, you want to use a symplectic integrator. So it's not like there's just non-stiff and stiff. There's also symplectic, Bethune-Coutts, Nystrom, exponential, and all these other things that can come up. And so if that's the case, you might think that, okay, extensive differential equation solver support is just about adding more equations for all the different cases that show up, right? And so, you can start to go, okay, well, there's SDEs as well. There's random ODEs, there's differential algebraic equations, there's different types of delay equations. But again, it's just adding a solver, right? Maybe not all PPLs have gotten there yet, but everyone can just keep on adding solvers, right? But it's actually there's a bit more to that. I want to show the Cartesian pendulum, right? Most people, when you try to solve a pendulum in some class or something, you usually cheat, right? You change everything to Euler's angles and then you solve that. So what happens if you actually try to solve a pendulum in Cartesian coordinates? This is actually a classic problem in the DAE solver literature, which is classically one of the hardest things to do. Pendulums are really hard. I think that most people don't know that. And so let's actually look at the pendulum equations, right? So the change in time in the x direction is velocity in x. Change in time of velocity is the tension of the string times x. All right. Now you have same with y, and then you have the constraint that your string for your pendulum is constant length. So x squared plus y squared minus l squared is equal to 0. Right. So this is the differential algebraic equation now for the two-dimensional pendulum in Cartesian coordinates. And it turns out that if you send this into any differential equation solver, except for a very special one, Glimda, it will actually fail. And the reason why it will fail is it'll give you a singularity. It'll basically tell you that it cannot invert this equation because the Jacobian is not invertible. The reason why the Jacobian is not invertible is because you have one algebraic condition here, but you don't have your algebraic variable tension actually show up in this equation. Right, so it's a minor detail. This is something that's called DAE index, right? This is a higher index differential algebraic equation. And what you're supposed to do is you're supposed to understand that this is a index 2 DAE. And so if you differentiate this equation, then you have x prime, y prime. You then plug in your other terms for this. Then you end up with this form equation, right? Exactly the same equation, just rewritten where your constraint is differentiated. And now this actually has tension show up in the equations. So therefore it's a equation that won't get you a singular Jacobian, right? And so this is something that will happen in equation solver spaces, and there's a lot of tools in like Modelica, Modeling Toolkit, that are built to be able to handle the kinds of numerical difficulties that show up here. And so, for example, if you look at this equation, right, if you just write down a Cartesian pendulum and you send it to a differential algebraic equation solver, even including ones like IDA and sundials, you'll actually get that the solution's unstable and it'll fail. The reason why it's unstable is because you have a singular Jacobian. Because of numerical errors, it might not think it's singular. It'll try to invert it, but it'll be very close to singular, and so you'll have some wild solution to a linear system, and then that will cause it to have to shrink delta t's because it thinks its errors are large, and then it'll tell you I had to exit because of this behavior, right? Whereas if you have a system, for example, that can do this kind of transformation automatically, like Modeling Toolkit or Modelica tools, then you can transform it into, well, it's just a pendulum. You can transform it into a ODE that is so simple that a non-stiff ODE solver can solve, right? And so I think that this is one of those things where it's just like, okay, you could keep on adding more equation solvers, but there are some behaviors of differential algebraic equations that can require other types of analyses in order to be a solvable form. Now, another type of thing that can show up is that you can just require a lot of customizable behavior. So here, for example, is a discretization of a two-dimensional partial differential equation. This is the Brusselator equation. So it's a stiff ODE essentially appended to a partial differential equation term. Exactly how you get this giant loopy thing doesn't necessarily matter, but the core is that you can just solve it with a stiff ODE solver. But the first thing that I'm skipping over here is that you need to make sure that you get the sparsity pattern of this ODE. If you don't have the sparsity pattern, this thing is basically in the 30 seconds to solve. So first of all, you need something that can run through code, detect sparsity, and be able to find and generate sparse patterns for Jacobians. Otherwise, it's not very solvable. But then you need to do things like be able to change your linear solver to KLU, because so when you have a sparse matrix, there's more than one type of solver for sparse matrices, depending on fill-in properties and sparsity patterns and such. And on this one, KLU is more efficient. On other problems, UMFPAC is more efficient. On other problems, et cetera, et cetera. In fact, there's an entire literature about just what numerical linear algebra to do for the different sparsity patterns. And so, then you might want to change to an iterative linear solver. And then not only do you want to do an iterative linear solver, but maybe you want to do an iterative linear solver with a incomplete LU preconditioning. And, you start slapping all this together. And, so when you really get down to the nuts and bolts of PDE solving, this is the kinds of things that people are doing. If you want to hear more about this, I just gave a talk yesterday at JuliaCon on linearsolve.jl that goes into all the different issues that can show up with linear solvers, right? So this is just all the different ways to change the way that you do the linear solving that shows up inside of a stiff ODE solver that gets you, the extra mile, the extra 3x speed up, but this is the 3x speed up of the thing that's already, 100 times faster than, using a dense Jacobian. And this is all without even mentioning partial differential equations, which of course, as when you get to partial differential equations, there's many different ways to discretize a partial differential equation into something that's solvable. Okay, so at that point now I'm just ranting, so I'll cut myself short there. The point is that equation solving is a huge topic, right? You think about, there's a community that's just as big as the probabilistic programming language community, people building out all these packages for it. And so this gives you kind of an issue, right? Because it's not like it's if you want to support the entire equation solving community, how do you, inside of a probabilistic programming language, it's that part of this code can be as big as the probabilistic programming language itself, right? To handle all these different cases, and to do all these things like DA index reduction. So how do you go about integrating that with PPLs, right? So that's where we get to the second part of the talk. What does Turing actually do, and what does that mean about its developer community? To contrast it, I'm first going to showcase what the gold standard here. What does Stan do? The one that I grew up on. What did I get to know first? And so if you take a look at the Stan user guide of today, what you'll see is that there's a section on ordinary differential equations, and there's a section on differential algebraic equations. And it says, here's the standard solver, here's the stiff ODE solver, here's the way to handle differential algebraic equations. For the different cases, you have 4 different ODE solvers available. It doesn't have the symplectic methods, it doesn't have all the exponential integrators and everything, but it has your standard non-stiff method, you have your standard stiff method. These 2 are from sundials, just wrappers to there. This one I think is implemented directly, and as well as the cache-cart method. Now, this means that it is missing a lot of these other methods that I mentioned, things like integrating with KLU and IOU preconditioning, algebraic multigrids, right? All those things that I mentioned are essential for a lot of these different cases. Also, that means it doesn't have the DA index reduction, right? The section on index of DAs essentially mentions that, hey, if you have a DAE that is higher than index 1, please rewrite it, right? Because without a set of extra tooling, doing that rewriting is difficult, right? So here's the real question. Okay, but it doesn't have all the features that say something like I would want with differential equation solving. But I think looking at why it doesn't have it is much more important, because that tells us about the development and what can be done and what can be done differently about the development style, right? So the key to why this is the case, to why these choices are made, is because probabilistic programming languages need derivatives when doing things like Hamiltonian Monte Carlo, right? You need to be able to define a Hamiltonian, and so you define what your momentum function is, and then you need to be able to solve the Hamiltonian equations, right? Basically what this means is that every single thing that you write into a probabilistic programming language, right, needs to have some way of being able to tell you, what is the derivative of this, how is either the forward derivative or the adjoint defined. And that becomes fairly limiting, right? That means that you need to make sure, say, if you add in a differential equation solver, you either need to add in rules for differentiating the differential equation solver, or you need to have a differential equation solver that has such rules defined, right? When you go back to here, right, I mentioned that these 2 come from Cohen and Hindmarsh, right? It actually comes from Hindmarsh's library, Sundials. And Sundials is well known as an ODE solver package in C++ that has forward sensitivity analysis and adjoint sensitivity analysis, which are essentially ways to do forward and reverse automatic differentiation of that ODE solver library. So the fact that was chosen as the one to use for the stiff ODE systems is not surprising, right? It's probabilistic programming languages need derivatives. This library comes with derivatives. So therefore, the choice for stiff ODE solver is the one that comes with derivatives. And so the key is that you cannot just stick any other ODE solver in there and have it work, right? You cannot just go straight to like say, oh, SciPy has this list of solvers, so let's wrap SciPy in there. I mean, if you do that, someone would have to go in and manually define derivatives for this ODE case, right? Now, this is where we start getting to the Julia part of the talk, right? And the interesting thing with Julia is that Julia has a pervasive language-wide system for differentiable programming, right? And so there is a single system defined by chain rules, such that no domain-specific language is required. If you use an automatic differentiation system like Zygote that uses chain rules as its base, then any Julia code that you put into the system would be able to support differentiation. So Turing.jl, for example, is a library where it's a probabilistic programming language. It needs derivatives, but its core DSL form is Julia code. And since Julia code has this language-wide differentiable programming system, it can just call, let's say, zygote on that code and expect to get some derivatives. Now, there's some cases that won't be supported. So, for example, zygote doesn't support mutation well, and so it's not like every single code will be differentiable. But it means that the domain-specific language of codes that support derivatives are things that are just normal Julia code. And this is where we start to diverge from, you look at Stan and it has this top-down support where it says, these are the things that we've added to the language that are differentiable and can be used in our PPL. This right here is the fundamental fact that then sends Turing in a different direction, because now it's just, we have a programming language that is differentiable. So if you put code in there, it should be okay. And so what does it look like in practice? Well, here, I was mentioning the differential equations.jl solvers, just the standard solvers that we have in Julia. And if you just stick that solve command inside of a Turing model, right? This is now a solve command inside of a probabilistic programming language, in Turing. If you stick that together, now you have Bayesian probabilistic programming on the ODE solver, right? And it's using nuts here, right? So it's using Hamiltonian Monte Carlo with a no U-turn sampler. And you can ask Hong. I did not, we did not collaborate to be able to get this put together. This comes together because of the composability of packages due to this fact of having a pervasive differentiable programming system. So the two of us work together without having to work together. And so this doesn't just come from with the differential equation solvers, right? You have the whole SciML ecosystem, which is all about tying into this whole differential programming support. And so things like nonlinear solves, integrals, and all that also get supported. And so the differential equations include stochastic differential equations, delay differential equations, and all of that. And so just to kind of showcase some of the ways that we've been making use of that is we've been doing things like defining ODEs with neural networks inside of there called universal differential equations. And so that way, this is a ODE with a partially known dynamics, partially unknown dynamics. And what we can do is we can probabilistically recover what is the missing function of someone's physical equation. We can then mix that with symbolic regression tools to be able to tell someone what is the probability of missing, what is the probability given this data that you are missing a quadratic term in the ODE that you've written down, right? Or inside of a partial differential equation, say you only know that there's a diffusion, you don't know what the nonlinear term is. You can represent the nonlinear term with a neural network, and then you can do Bayesian, do Bayesian neural networks over this neural network to find a differential equation. Once you recover that, then you have a representation of a functional form that's missing. And then you can tell someone that there's a 73% chance that the missing equation here was quadratic, a 27% chance that it's cubic. If you want to know more about this exact automated physical discovery, please check out my other talks on scientific machine learning, and I can point you to the right talk on this piece. But yeah, so we've been able to do this in a way that's mixing the Flux neural network library with the differential equation solvers, just because of this fact of pervasive differentiable programming, right? We can just the Turing does not need to support anything that we want to do. We just go do it if we know that it's differentiable. Now, what is the downside to this? The downside, of course, is documentation. In fact, the interesting thing here is that the Turing documentation API or the Stan API documentation on differential equations is much more extensive than what the API documentation of Turing on differential equations, right? The reason is because there is absolutely no documentation of Turing on differential equations. The only thing that you'll find in there is one tutorial that I added to the Turing documentation that says, oh, hey, you could use these solvers inside of Turing. Right. And that's one of these big downsides, right? Because of pervasive differentiable programming, you no longer have the PPL actually adding differential programming support or differential equation support. And so therefore there is no thing to document, right? It's just you use this other library that has its own documentation, you take it, you put it inside the PPL, and you can expect it to work. But I think that there's then a major signaling issue of, okay, if you have a system that just does composability, how do you actually signal to people that they can actually do that? especially if they come from a previous language where was top-down support that required that someone put these pieces together. They would normally add a documentation to the PPL that says, hey, we support these differential equation solvers, but because of this composability, that will never be there. And so I think it's interesting to really highlight that, this documentation issue is kind of fundamental to how the development has gone. It's not that it's just missing API documentation of the differential equation solvers. It's that the way that it's developed will make it so that way the true documentation of the differential equation solvers is go look at their documentation. The documentation of differential equations.jl is about as long as stands itself. So there's no reason to embed it as like a little tab inside of Turing, but that causes its own issues for new users joining this ecosystem. And so, I mean, the upside is that you get all the features, right? Here's a delay differential equation solver slapped inside of Turing. You can get the delay differential equations, you get the SDs. It's just, there's nowhere in the documentation where any of that would go. It's just, you would have to know that you have this automatic composability. These things are differentiable in SciML, so therefore they can be added to Turing. What you get in the end is you get something that has, a lot of features, and you have something that is fairly fast, right? So you can look at a lot of the papers that we have on accurate and efficient physics-informed learning that talks about how, when I mentioned that there's adjoint methods and derivative, so there's actually about 8 to 9 different ways to be able to calculate derivatives of ODE solvers. They change performance by about 3 orders of magnitude. And then there's a lot of different details, like, for example, when you use, we use a lot of tools like enzyme for handling mutation well inside of our systems. Enzyme is faster than JAX by quite a bit. And not only is it faster than JAX, in order for JAX to get close, it needs to actually disable reverse mode automatic differentiation. And so for very large systems, you actually have a major asymptotic difference between what the Julia differential equation solvers can do and what they can do inside of a PPL for derivatives versus other systems. And one major reason for this is because a tool like JAX will apply the automatic differentiation before doing compiler passes, whereas these tools like Enzyme actually apply the compiler passes before doing the differentiation results, and so you actually get asymptotically faster gradients in a lot of cases. Now, but at the end though, the issue that we will have, and I think that we'll continue to have, is that there's no ownership to the documentation, right? I showed you what it looks like in the Turing documentation, where it's differential equation solving is a second-class citizen because it's just a tutorial that says for any information, go look at the differential equation solver docs. And in the differential equation solver documentation, it says, well, we don't do Bayesian estimation. Go look at the Turing docs, right? And I think that that's where I'll end, because this is an interesting result, right? Where you would think that all this would give you functionality for free is documented by no one, and so it's its own problem itself. And this is, I think, the thing that we need to understand with the Julia ecosystem, and one of these next frontiers that we're going to be looking at. So, multiple dispatch and pervasive differential programming are amazing features, but we do need to counter some of their downsides. So yeah, so thank you very much, and I'll take some questions.
So how do we?
Raise your hand.
I'm not sure how to do that.
Reactions.
So was that a question, or heard someone?
Yeah, no. How are we taking questions? Sorry, can people hear me?
Oh, you can just speak out, or you can write it in the chat. But since
okay.
I can hear you.
Oh, I tried raising my hand on Zoom. Hi, Chris. So that was a really nice talk. Thanks so much for talking about this, which is something that's been a problem for us in Stan, sort of doing this kind of integration you're talking about from the get-go. One of the things I was curious about, like when we started Stan, what we did is just auto-diffed straight through the algorithms. We were like, okay, we did essentially what Julia does all the time, which is we take, at least I think what's going on, which was we took the C++ out of Boost to implement the RK45 thing. and then just auto-diffed through that code, which took up like an exceptional amount of memory and didn't give us particularly accurate derivatives, but was enough to solve like pharmacology problems we cared about. And then we went and actually built in our own like coupled system that actually coupled the ODE system so we could control error, right? So I'm getting to the question here, which is when people write this library of solvers, how do you know how much error control there is on the derivatives? Do you just auto diff through their solvers, or are they all writing custom sensitivity code in the ODEs? And how do you discover that? Like, how do you discover which of these ODE solvers will work well with the auto diff system?
Yeah, so yeah, that's a great question. So first of all, so the way that's done in the SciML ecosystem, right, is that there's one interface, and that interface function, so the solve function itself has the derivatives defined on it, right? And so if you go, if you see a solve command and you differentiate it, then that means that any choice of differential equation solver always will take that path. So it doesn't matter if it's a pure Julia code, a C code, or a Fortran code, it has some kind of overload that's being done. Now on forward mode automatic differentiation, it will do a bypass where it says, oh, please just differentiate the algorithm. The reason why is because in this paper right here, we showcase that differentiating the algorithm for forward mode automatic differentiation is a lot faster because your derivative terms are always very related to your primal, right? You know, the derivative of cosine is sine, and so you know your automatic differentiation engine might specialize on that and just compute sine cos, right? You know, it's one of these internals in a lot of languages, and so it might compute the sine and cosine at the same time and then split the terms, right? So
yeah,
you want
for us, we can statically unfold forward mode, so it's much faster.
Exactly. So you want to do that, but yeah, but then you have the error control problem, right? So what you can do there though is that you can actually go into the rules of the differential equation solver, and you can change the default rules so that way the norm that it calculates is a norm that includes the dual terms of the forward mode automatic differentiation. And if you do that, that's equivalent to the error control that you would have of the forward sensitivity analysis. And so yeah, so there is like a little trick inside of the differential equation solver that's done, so that way it's actually able to get proper error control of the derivative terms. Otherwise, there are some cases that I know of that you know, there are cases that I use to kind of showcase on some you know differentiable solvers that you know there are some cases where the primal can be solved exactly by the ODE solver, so it actually just grows its steps to infinity, but the derivative term is not able to be requires error control, and so the derivative calculation is basically infinite from if you don't do this change of the norm. So yeah, so we make sure to do this change automatically in the back end. There is a way to be able to control the norm to be able to turn that off, but I don't think any user ever really knows to do that. And we always want to give them the correct thing to do, so we do it by default. Yeah, and then for reverse mode automatic differentiation, the story kind of flips. This paper is all about that. So it's just a comparison of automatic differentiation and continuous sensitivity analysis. So it's just a whole bunch of benchmarks on you know the different ways to compute derivatives of differential equations. And in the reverse mode case, what you find is that you know the adjoint methods end up being a lot faster than the handwritten ones for various different reasons. Because they can basically cut down. They don't have to do the same steps going backwards and everything, but they do have less accuracy. Adjoint methods can very easily run into accuracy issues. And so then you want to have different choices there of you know different ways of computing the adjoints that are some are more stable than others, but then also be able to directly differentiate the algorithm when you want to go back to the slow but accurate form. So yeah, so there's a lot of things that go on with having to choose how to differentiate the solvers. In fact, there's a bunch of different ways to do adjoints, but that's not even getting to the chaotic case where you know when we look at chaotic systems, there's a whole different set of methods you have to do because you can no longer trust that your primal pass is correct. So that has something called shadow adjoint methods, and yeah, that's a whole topic of its own. Yeah.
Great, thanks.
Thanks for the very good question. In the interest of time, I guess we're going to go along straight away to Maria's talk. So this is about program analysis of probabilistic programs. perfect fit